What I would like to do today is to show you one of my research concepts, and I'm looking forward to your comments to see how you, people that are related to practical things that are made for today's networks, today's devices, can relate to my concept that come up a little bit into the future. So I will be talking about fungible devices and ubiquitous applications, which is related to my research on multi-device applications. Those are applications that are able to communicate with the user through multiple devices at the same time. So you can have an image on a TV screen, audio through your headphones, and navigation using touch screen on a smartphone. All within the same application, all within the same functionality. So what I want to show you today is two terms related to this, fungible devices and ubiquitous applications, which are a little bit closer to the concept of cross-platform applications, which is tightly related to multi-device applications, but is in a more narrower way. Then I will show you existing solutions that you know for sure, but I will show you how they don't work, in my opinion, and why we should look for another approach. And the new approach I want to show you is called device-independent architecture. It's a little bit different approach to designing applications for mobile devices, which allows us to overcome the obstacles related to cross-platform applications and also enables multi-device applications. And I will show you some new possibilities that come with this new architecture. So the ultimate goal is simply to provide a given functionality to our users through any end devices, be it an iPhone, an Android phone, or a Tizen phone. If you develop an application, you want to have the broad range of users, no matter what devices they are using. And from this point of view, the problem is how to get your application running on every possible device. This can be solved by the concept of fungible devices. The word fungible is used to describe goods that are exchangeable, that can be used instead of another one. For example, a bread from one bakery can be easily replaced by a bread from another bakery. So in this sense, fungible devices are devices that can be easily replaced by any other device, allowing for the same functionality. So the user can easily switch from one device to another and still use functionality provided by our application. What is important here is that it should be done without the need for multiple variants of the application to keep the costs down. Of course, not all devices can be fungible. Devices like in-vehicle infotainment units are not fungible with laptops, or smartphones are not fungible with smart TV. It's mostly because their purpose is different. Users are using them for different activities in different contexts. So usually they don't expect the same functionality on those different devices. And also, because of this, their equipment and capabilities differ significantly, and we cannot talk about those devices as fungible devices. Devices that are usually seen as fungible are devices like smartphones and tablets, or tablets and laptops, or laptops and desktop PCs, because they are mostly used for the same activities. The difference between them is the context in which they are used. Usually, you use your mobile device in a mobile context and your laptop or a desktop PC in a fixed context. So you are using it in a different way. Smartphone is used usually in a hurry, in a different conditions, and when you sit at the laptop, you have more time to explore, search, and find your functionality or use your functionalities. So the purpose of use is similar, but those devices differ in capabilities and interaction modes. So this influences the way the user interface should be designed for those devices. So even if you can use the same application on all those devices, providing the same functionality, you have to take into account that the user interface of those applications on different devices have to be different. So we can say that those devices are almost fungible. You can provide the same functionality, but you have to provide some modifications to the applications to actually do it right. So what devices are truly fungible? Can be truly used as equivalents. We can refer to the same kinds of devices, like switching from a tablet to a tablet or switching from a smartphone to a smartphone should make the thing a lot easier. And it is possible to some extent within the same range of devices when you have similar hardware or similar software. But when you take into account the whole range of diverse devices that are on the market, you have a lot of hardware differences, especially differences that are visible to the user, like the screen size, its resolution, pixel density, aspect ratio. All this influences the user interface of the application, which has to be implemented differently on different devices. Also, availability of different sensors or hardware capabilities is different between different devices. On one device you have NFC, on another device you don't have NFC, and it's not always possible to provide the intended functionality on every device. Also, another layer of complexity is enforced by differences in the software layer. Different operating systems force you to implement your applications differently for different devices. Even if you have the same operating system on different devices, if the version differs, you also have different APIs and different possibilities on different devices, which can be clearly seen when you take a device with Android 2 and Android 4 to your hands. There's a huge difference between those two, and in terms of devices and in terms of UI patterns. So actually, to have truly fungible devices, you need to have hardware uniformity, where you have the same equipment and similar parameters of the hardware, like the same aspect ratio of the screen or similar processing capabilities, so you know that your interaction will run more or less naturally for the user. Also, you need to have software uniformity to be able to provide the same look and feel of your application or provide the same functionality. And it is possible to some extent to have such devices, like the Apple ecosystem created such environment in which you can switch from one device to another, more or less taking your application with you. You can switch from iPad mini to iPhone and still use the same application, just scaled to the different screen. Also, to some extent, it is possible with devices from the same family from a given vendor. For example, Samsung with their Galaxy devices provides the same capabilities within different devices, like the Galaxy Mini and the full Galaxy. It's almost the same, just the processing power differs. So actually, truly fungible devices are currently possible only within a closed ecosystem, like the Apple ecosystem where you switch from iPad mini to iPhone, or within the same device, where you switch from one Nexus 7 to another Nexus 7, you are sure that everything is the same, those devices are fungible, they are equivalents, and you can easily provide the same application in the same way on both devices. So those are truly fungible devices. But such fungibility is possible only in closed environments, in corporate solutions, in industrial developments, where you can control what devices are used by your users. Then you have the truly fungible devices, and you have the platform to provide your functionality on every device. But in the real world, fungibility is not possible. In the real world, the range of different devices, different operating systems, fragmentation in operating system versions is so high that it's not possible to have a uniform platform. So we go back to where we started. How to provide the functionality of your application on any device where those devices differ significantly. The second term I want to talk about is ubiquitous applications, where the ubiquity means that something is available every time, everywhere, is omnipresent. So ubiquitous application is an application which is always available to a user and provides the functionality no matter which device is used by the user, possibly synchronized across all devices. So it's a little bit more than just cross-platform application. So the question is how to build such ubiquitous applications in the world of non-fungible devices. And you already know different approaches to the problem. You use it daily. You can build multiple native applications. You can build cross-platform applications, be it either with cross-compilers or a common runtime. Or you can use web applications. All those solutions have their pros and cons. And I want to highlight some of these and talk why, in my opinion, they don't work properly. They don't provide the uniform platform for ubiquitous applications. So multiple native apps provide good performance because they are much closer to the hardware, and you are able to optimize your code to run it in the best way. Also, you have the access to all possible hardware features of your device because you have direct access to the operating system API. And what's also very important, you have access to application markets, which makes it easier to distribute, publish, promote, and simply monetize your application. All this comes with a cost, and the cost is most related to the development and maintenance costs, because you have to develop your application for each single platform. You have to make a copy of the application for an iPhone, another implementation for Android, another implementation for Tizen, and so on and so on and so on. There are, of course, ways to avoid this using cross-platform approaches, but I will talk about this in a moment. When you want to have a native approach, you have to implement it separately on different platforms. And this generates huge costs because each platform requires different skill set from developers and also uses different UI design patterns. So both the implementation and the UI design has to be different on every platform. Also, what has to be considered is inconsistencies in API of different operating systems. You can implement a native application on iOS and the same native application on Android, but those two operating systems have different APIs, and not everything that is possible on Android will be possible on iOS, and vice versa in some ways. So not every time everything is possible on all different devices, even using native approach. Cross-platform applications drive the cost down because they provide a consistent platform for your application across different operating systems, across different devices. So you only need a single implementation of your application. Also, you need a single skill set, developer skill set, to build the application, because you do it only once in a given language using a different project structure and specific tools. So the costs are significantly lower, and you can also use application markets to promote and publish your application. So it's all better in this regard to native apps. But it comes again with a cost of worse performance. It is, in most cases, the performance is worse because of the underlying layer which adds complexity between the operating system and the application, or because the cross-compiled code is not optimized as it should be. So in most cases, I don't say that it's always the case, but in most cases, cross-platform applications are slower than their native counterparts. Also, when you use a specific cross-platform tools or framework, you are restricted to their own operating way of doing things. You have to use a specific programming language, you have to use a specific project structure, or you are fixed to some limited UI capabilities. This creates some kind of a platform lock-in, which closes you to some solutions that could be possible within different cross-platform tools. Also, cross-platform solutions usually have a more restricted API than the API provided by the operating system. And almost always you have to wait a little bit to access the newest features introduced in devices and operating system, because you have to wait for the vendor of the cross-platform tools to actually implement API for it. So you are always lagging a little bit behind. So it's not also the perfect solution. The third option, to create web applications, it's extremely popular because you can assume that the runtime is already existing on almost every device. Be it a web browser or a built-in web runtime, you can assume that it is possible to actually run web applications almost everywhere. But to me, web applications are just another way of implementing cross-platform approach. You have a common runtime, which is the web browser. You have a single language set, which is the HTML, CSS, and JavaScript. And you have an API provided by the web browser or the web runtime, which is fairly consistent within the specific set of runtimes, but it's again quite limited. Of course, this comes with all the drawbacks of cross-platform solutions, like performance issues and API restrictions, and also, what is not mentioned on the slide, inconsistent implementations in web browsers. Different web browsers implement APIs in different ways, so not always you can assume that and functionality implemented in a certain way will work this in the same way on every browser, on every web runtime. Usually you have to use some hacks to avoid this, or multiple versions of some code passages to accommodate this. And in most cases, web applications cannot be put on directly on marketplaces. On some platforms it's possible, but not always. So usually we assume that web applications are distributed in another way, which makes it harder for application developers to actually get those applications to users. But again, for me, web applications can be seen just as another variant of cross-platform approach. So those two approaches to the problem of non-fungible devices have their drawbacks, which is the increased cost of multiple native apps and worse performance and platform locking for cross-platform applications. And what we are doing, we are trying to find a solution which would allow us to implement an application once, avoiding the high cost of implementing all the native versions, but staying away of platform restrictions caused by cross-platform tools. And the way to do it, to have those diverse platforms separated from diverse devices, is not very hard. And actually, this problem is known in distributed systems for years. The separation is usually done by providing some universal middleware layer, which makes both sides transparent to each other, or through a standard protocol, like the TCP or UDP used on the internet, where a single protocol is used to communicate all those different devices that are used on the internet, no matter what this device is. It only matters if it implements the same protocol, the same language. So using this approach to separate those two concerns, we came up with the concept of separating applications from devices. We can put something between applications and devices to make those two transparent to each other. Application developers won't have to care about what devices are used to actually run their applications or provide the functionality of their applications. And devices can be developed without any relations to different applications. And as with every separation, the main problem is where to draw the line. Where to draw the line between applications and devices. The common approach used in existing solutions is to draw the line at the API level. So on the one side, you have the application. On the other side, you have the device and the platform, which is used to actually execute the application. And we already know from what I showed you that this doesn't work very well. So my idea is to move the separation to a different point, to separate devices and application and platforms together. So instead of abstracting a platform, we are abstracting a device. We are treating all devices are in the same way. It's not easy because we already saw that there are no fungible devices. So there is a need for some kind of abstraction on top of different devices to allow us to see all devices in the same way. So when you look at the device which is running an application, we can differentiate different concepts, different device components that are used by the application. So the application uses processing resources like CPU, memory, storage to actually execute its code and process its data. The application communicates with the user using different user interaction channels, like a screen to present the information, or speakers to play some audio, or touch screen to receive some gestures, or sensors to sense the orientation of the device, or different gestures done with the hand of the user. So those are user interaction channels, in and out. And also there are another sources of information that can be used by the application, and those are usually sources that provide data about the environment in which the device is used, about the usage context, about the time, location, light intensity, and so on and so on and so on. So they are not directly related with the user, they are not directly influenced by the user, but they sense the environment in which the device is used. And when you see the device in this way, at this abstraction level, what you can notice is that only the user interaction channels and information sources have to be close to the user, have to be embedded in the device. The application and the processing resources can be easily placed elsewhere. So we can draw the line here. We can separate the device and actually take the application out of the device, execute it elsewhere, and just standardize the point for connecting to user interaction channels and using information sources. And this is the main idea behind device-independent architecture we are analyzing in our research currently. We are treating a device merely as a gateway to the user, only as a collection of user interaction channels and sensors that allow us to sense the usage context. All processing and application execution is done elsewhere, usually on some kind of a platform as a service. And this approach gives us a few advantages. First, the fact that the application is executed outside of the device allows you to use any platform, any programming language you are familiar with. Also, it allows you to have only a single implementation of the application. Because you have a single runtime, single platform, you only have to implement the application once. So we avoid the problem with native apps. The fact that we access all the sensors on the device in a universal way allows us to do it in the same way for every external service, not only those information sources provided by the device. It could be done in ways that are already known and used. For example, for one-time access, you can use REST approach. For continuous monitoring of some information sources, you can use observer patterns. So simply choose what you want to know and at what interval. And the fact that we are not using a specific device by a set of interaction channels allow us to build the user interface on a little bit higher level, on a more abstract level, which makes it easier to build it only once and enables a way, or enables us to build or employ multiple different UI generation patterns. So the user interface generation can be done in a standard way, where, like with web browser, you send the UI description to the device, and the device actually interprets the UI described in HTML and CSS and renders the UI on the device. But it can be done also in different ways. For example, the application can render the whole user interface and send only image to the device. or a video stream. This is already happening. I don't know if you are aware of a cloud gaming platform called OnLive. Anyone heard of it? Okay, quite a few. They are using exactly this approach. They are running the game on their servers, and they are streaming the video from their servers to the client on your machine. So there is no game processing on your computer. You only see the video feed from their servers. This is exactly this approach for UI generation. And also there is possible to build in multiple hybrid approaches, like building a generic UI generation middleware, which will take an abstract description of a UI on the one side and will generate a final UI tailored for a specific device on the other side, taking into account device capabilities, user preferences, and the context of use, for example. So much more possibilities for building UIs emerge from this approach. You don't have to build in everything into your application. Currently, we are researching different aspects of this approach in our research projects, and I will show you a few examples. In one of the projects related to using software-oriented architecture for multiple different business processes and services for end users, we are focusing on providing user interfaces to web services, or speaking differently, to business processes implemented with those web services. So we had a middleware which was completely transparent and agnostic, business logic agnostic, independent of the business logic implemented in web services. And what we did, we took the information about what should be shown to the user, and using some patterns and templates, we generated a specific UI for a specific device. This way we are able to generate UI for desktop PCs, laptops, tablets, smartphones. The same functionality provided in a different way for each device, conveniently. Also, what was possible to take into account user preferences and usage context. For example, location could influence the sorting of items on a list. One of the applications was related to building construction, where the construction manager had a list of all the construction sites, and for example we could use the location of the construction manager to sort all the construction sites according to the distance from the current location. This was one example of using external information to influence the UI of the application. Of course, there were a few issues. One of those was how to gather the information about the context of use. When you use, for example, a web browser on the client side to render the UI, there is it's not that simple to actually take all this information and send it with the request to make the UI know what is the context. You would have to change the HTTP request and put some additional HTTP headers, what we actually did. Otherwise, you have to go back and forth asking for another set of information. Also, another problem we had in this project was that when you want to store and model user preferences, it's perfectly possible for preferences that are generic and that are related to the user itself. Like, I want to have bigger texts because of my sight problems, and so on. But if those user preferences were related to business logic, we had to refer to an external service which stored those preferences elsewhere, because we wanted to keep the middleware business agnostic. Another example is a ubiquitous project we do for ABB, where we are researching UI adaptation middleware in terms of how to describe a UI in an abstract way, how to build generic, universal UI adaptation rules, again, that are business agnostic, so they can be used for any application, again and again. How to gather device capabilities without asking the device directly, and how to render the final UI tailored for a given device, changing, for example, the format. From one device it should be HTML, but for another device and different client it should be XAML because it's a Windows Phone client, for example. So in this project we had a few issues with the generic adaptation rules, because you can provide a set of generic rules, but it will limit the expressive power of the designer of the application. So what we did, we created a way to actually extend those generic rules with rules that can be fed from the application. So the application can hint how to actually interpret and generate different parts of the UI. Also, for the information about device capabilities, we have used DDR, device description repositories, like Wurfel and Device Atlas. And what we find out is that they are not very accurate, at least to say, and they're usually quite outdated. And in production environment, you cannot rely on it for a proper information about device capabilities. You have to either ask the device directly, or you have to constantly update the repository about different devices that can be used. In the context of this project, it was enough to simply update the repository, because the range of devices that can be used with this system is limited. But otherwise, it would be necessary to ask the device for its parameters. What is interesting in this project is that this approach also allows us to migrate the UI of the application from one device to another, to allow the user to start implementation of the usage of the application on one device, and then just leave it, pick up another device, and continue at the same point where it left off on another device, including all those user interaction changes, like starting typing a message in a form field without submitting the whole form. It was very nice, and it showed that it gives new possibilities than just simply solving the existing problems. In another project we do for Santander, within the Santander Universidades project, program called UBank Apps, we are researching cross-platform, or not, usually cross-platform solutions for banking applications. So here we are targeting specific platform. Those are touch screen devices like smartphone and tablets, and we are researching best ways to describe the UI in a way that is screen independent. So it doesn't know what is the size of the screen, what's the aspect ratio of the screen, what is the pixel density of the screen, because this also have to be taken into account to render the text higher or smaller. And also we research how to translate this into a final UI, which is tailored for a specific device, which is a description which actually tells the device that this specific box should be placed 20 pixels from the top and 50 pixels from the left. And this generation can be done using information about the device and about other possibilities. And in this project, we have analyzed a number of existing user interface description languages, from high-level languages like UZXML, UIML, and so on, to low-level platform-specific languages like the XML layout language used in Android, or XAML, or XUL, provided by Mozilla. And what we found out is that none of them allows to fully describe, declaratively describe the user interface. If you want to describe not only the look and layout of the user interface, but also the behavior of the user interface, simply in terms what should happen when I click this button, you usually have to refer to some programming languages. You cannot do it fully declaratively, which makes it harder to simply create a declarative description of a UI and send it to a device for presentation. We also do some experiments on different aspects of the architecture. For example, we did an experiment with the user interface generation where we compared Windows Phone application generated natively and the same application but implemented according to device-independent architecture, which means that the whole application was on the server side and the user interface generation was on the server side. We used the same devices and same UI patterns. So the look you have at the bottom is the same for the native application and for the device-independent application. And the times that were seen from the user perspective to get the response after some interaction, you have on the chart, native ones are the blue one, device-independent ones are the red ones. It was 7 to 8 times slower to generate the UI on the server side and send it back to device for presentation. But still, it is under 100 milliseconds. So it is almost indistinguishable for a user. And the amount of data you have to exchange between the server and the device is not that big actually. Because when you use an application which relies on data provided by an external server, you have to download the data, analyze it, and show it. If you have a device-independent architecture, all the data processing is done on the server side, and you only download the image of the UI, actually, in this case. And the difference in size between the data that have to be downloaded for the native application and the size of the image of the UI is not very high. With current broadband mobile connections, this transfer can be still under 1 second. So it can be still acceptable for users. Other benefits that can come with this architecture, and we are analyzing right now, is unlimited performance, because of the fact that you are executing your application outside on some scalable cloud. It's up to the cloud to scale the performance of your application. You can put as many nodes as you want, and it won't affect the application on the device, the functionality on the device. It will only make it faster. So you are not bound by the constraints of the device, which is very important, for example, for very processing-intensive applications like image recognition. In one of the projects we had AR application which did some extensive image recognition processing, and it was way better to do it on the server side. The user interactions were much more fluid. Also, this approach potentially could lead to a better battery life. I know that you will say that you don't process the application on the device, but you use the network much more than in a native approach. That's true, but at some point of the complexity of the application, the gain created by the fact that the processing is done elsewhere is higher than the fact that we are using the network much more. So for some applications, it could lead to a better battery life. And it also opens completely new possibilities that were not possible before. As I already said, it allows applications to follow users. Since the application is not bound to a specific device, you can easily switch the device to another one and continue using the application without any problems. It opens a whole way for shared devices or public devices, where you can access your own functionality, your own data, on not your own devices. Also, it opens a completely new area of multi-device scenarios, where you can use multiple devices within the same application, because the application doesn't see devices. It sees only a set of user interaction channels. So it can choose to send the image not to your smartphone, but to your TV. So we can explore completely new areas with this. Of course, this opens new problems, like how to detect what devices can be used, how to authorize those devices, how to communicate between devices without the need to push all the data through the server, and so on and so on and so on. And this is the ongoing research currently. But the possibility is there. And actually, we have implemented one of such scenarios together with Fraunhofer Focus. They were working on the EU project called Webinos, which is about building a multi-device web platform for applications. So you simply have web platform for implementing applications that can use multiple devices at the same time. So we combined this with the device-independent architecture, and we have built a solution which used a number of devices to provide functionality for a very simple prototype application. The application is called LifeLog. It allows a user to record electronic memories in the form of an image captured from the phone camera, audio recording, or just a text, along with the geographical location, and store it somewhere. And then the user can share the selected electronic memories on different devices, on screens, on tablets, on your friend's screen. For example, you come to your friend's house and you want to show him some of your photos. You can simply select his TV as the output of your application and simply show your photos on the big screen, not on your small screen of the smartphone. So it is already possible. So with this broad overview of the research concept, I leave you to think about new possibilities, new scenarios that could be implemented. If you want to know more about my research, you can contact me at the university, or if you want to talk about more product-related approaches, you can always catch me at my new startup, Ubiquitous, which provides tools and solutions for such kinds of applications. Thank you very much.
Have you done any testing about the bandwidth, the needed bandwidth to run through a day?
The bandwidth needed for the application to run on the server side and...
I mean, the user side.
Mm-hmm.
How much would it need to run application user way for the whole day? I mean, using your mobile phone?
Yeah, it actually depends on the way you implement the UI generation solution. Because if you want to, and actually it depends on the application also.
Yeah, of course.
Because if it's, for example, a game, you have to stream the whole video of the UI from the server to the device if you want to keep the whole separation. And it will cost a lot of bandwidth, essentially. So it's not very convenient for not broadband connections. But LTE is simply enough because smartphone screens are not so big, actually. And the resolution, even if it's so high, the density is quite high also. So you can provide a video with much lower resolution. So you can provide a video with up to 2 megabits per second, and it will be feasible.
Yeah, I'm more wondering about the limited bandwidth which most countries in Europe have. Like, most countries have like 1 gigabyte limited bandwidth for 1 month.
Yes, that's of course an important issue, and it limits the use of such kinds of applications for sure. But when you think about standard applications, when you have a more static user interface, you don't have to continuously stream the user interface.
Yeah, but you said you want to keep streaming the data from the phone to the server because you want to be able to resume the application from another device. So
yes.
If you're writing a message, you have to keep sending the message, for example.
That's right, but those are very small incremental changes.
True, but through a day, I was wondering how much it was.
We didn't test such scenarios, so I don't have exact data.
Yeah. Just to join to this discussion, I was working a lot in previous year in the smart TV area, and there was a problem of performance of the devices as they are very slow, and we was thinking about this type of cloud gaming and move as we show on the diagrams whole generation to the cloud and just put the client on the smart TV to receive key presses and just send it direct to the server and get back the video stream. But there was a lot of problems with connection delay. It was kind of 300 milliseconds. So it could be used just for kind of casual games or kind of nothing dynamic for the user, and a lot of bandwidth, which is really expensive from the server side when it comes to thousands of users. And HD screen in this smart TV. So it was really problematic stuff. I'm curious. Is it from a business point of view? Is it really valuable to introduce this kind of?
You are right. For applications such as games, where you need the immediate interaction, it's quite difficult because you have to keep the delay at least under 100 milliseconds. But as the example of online shows, it's possible with substantial investments in the infrastructure. But anyway, from the business point of view, I think this approach is much better suited for applications that are not so interactive, I would say. Like standard business applications where you usually have a static UI and you change different parts of the UI just by updating a small part of the whole image. So you don't stream the whole UI constantly, you only update it once a few seconds. So it's much more price-wise, I would say, for such architecture.
Okay, so now the main question. when there is no this streaming, you end up with kind of a markup language and the client application which can render this what you are sending from the server. So isn't like the same like Fungible that it has own library for the client, and it gives you the possibility to do once stuff for multi devices, or HTML which gives you the same on the browser.
Actually, there are different approaches to this problem, because on the one hand side you can follow the pattern created by web browser, where you simply send a declarative description of the UI to the client, and the client interprets the description and renders the UI. But on the other hand side, you can also render the UI on the server side and send only an image to the device. Then you don't have the UI processing on the client.
But what I'm curious, about because somehow you need to have this client application on every device. So you need to develop these clients for Samsung, for iPad, for iPhone, for everybody.
That's true. Currently, you would have to implement such client for every platform, but we see it as a problem of implementing support for a specific standard, like the protocol stack for the internet, where you have a standardized way of processing TCP messages. You could have such standardized way of processing UI messages. I don't think so. HTML is a little bit higher level, and it puts some constraints on the fact how you can actually build the UI and what is possible with the UI. I think such protocol should be on a lower level, where you deal with graphical basic structures, not such abstract structures like paragraphs, blocks, tables, and so on.
You said that the Fungible gives you the problem of that you need to wait for new releases of new features which device have. Now you
That's right.
implement it all, so still you don't have right away the access to the new features for the newest.
That's only true for completely new features. The idea is to have the protocol generic enough to accommodate everything. So even if there are some changes, for example, in the screen is bent and it has some different parallax effects and so on, the protocol should be generic enough to be able to accommodate this. We don't have the solution for the protocol yet, so, but we have some vision in this regard. Okay, one last question.
Actually, you've answered part of my question right before, but I'd like to know more about this abstract UI, the one you showed, the Santander project and the one before. How abstract is it? Is it like HTML with then different CSS sheets for each device, or is it something more abstract?
Actually, it differs. In the Santander project, we are researching different UI languages that allow us to describe the UI on different levels of abstraction. For example, UIML is very, very abstract. It allows you to construct like boxes and UI elements inside those boxes without telling what those are. So it's very abstract. But on the other hand side, we have languages like XAML, which allows you to tell that this is a button, this is something else, and this is very concrete with concrete font size and so on and so on. So it depends on the use case. Okay, we are out of time, so thank you very much. And if you have more questions, I will be outside. Thanks.